Good morning, everyone. We're going to get started back in the end of Chapter 5 today. So our goal is going to be to finish Chapter 5 and get into Chapter 6 today. So if we had sort of one last idea for trying to find an enthalpy of reaction. So let's imagine you're trying to find the enthalpy of reaction for some molecule like A to D. The ways you might go about finding this would be, well, if you could study this in a coffee cup, you could use coffee cup calorimetry if you wanted to find the delta H of this reaction. So if you're trying to find delta H, you don't know it, you could try to do like a coffee cup calorimetry problem. If this were some sort of combustion reaction, maybe we can use a bomb calorimeter to determine the enthalpy of this reaction. Another approach might be if we knew the A to B and the B to C and then the C to D, we could use Hess's law and sum those reactions up and get the A to D. But one last approach in this chapter is, well, what if we could tabulate the enthalpies of A and the enthalpies of things like D and just tabulate these for our reactants and products and reactions so that we could just very simply say, well, delta H would just be the enthalpy of D, the final state, minus the enthalpy of the reactant A. And in some ways, that would be exactly what delta H is. It's just whatever the enthalpy is of the products minus the enthalpies of the reactants. Well, what we end up doing is we do something very similar to this. What we're going to see is that we're going to take our delta H and make it equal to something we call the sum of the enthalpy of formation of the products. So we're going to take something called the enthalpy of formation of the product, D, and then subtract the enthalpy of formation of the reactant A. So we're going to take the sums of the enthalpies of the formations of the products minus those of the reactants. And it's going to be very similar to what we might prefer to do if we actually knew the absolute enthalpy. So this is probably how we would ideally tabulate enthalpies, would be to know the absolute enthalpies of all of our different substances and then just be able to plug those into an equation to find delta H. An alternate approach, though, what we're going to see is we're going to define a formation reaction. So we're going to define the formation reaction for forming a substance from its elements, where all the elements for the formation reaction on the reactant side are in the standard most commonly found state for those elements. So let's take a look at a couple examples. So let's look at CO2. So if we're trying to form CO2 from its elements, you kind of look at carbon, you look at oxygen, you say, well, what's the most stable state of carbon at room temperature? And the most stable state turns out to be graphite. Carbon exists in actually a lot of different forms. It could exist as diamond, which is a solid form like graphite, just a more precious form. It could also exist as like carbon nanotubes. It could also exist as like a buckyball, if you've ever seen kind of like a soccer ball of carbon atoms. So carbon has a few different forms, but graphite is the most stable. And so for forming CO2, we start from the most stable state of carbon at room temperature, being graphite, and then oxygen's most common state and also most stable state is O2, so molecular oxygen. And so we're simply just forming 1 mole of CO2 from its elements, and that formation reaction is going to be very useful because the delta HF, the enthalpy of formation of CO2, we can then use in problems kind of like it were its absolute enthalpy. And so the idea of enthalpies of formation is we can use them kind of like they're these enthalpies, the absolute enthalpies, even though they are a reaction of forming a compound from its elements. So we can have this for water. So water would be H2. And then it's actually okay in this reaction to have a fraction. This reaction here, we want to make 1 mole of product. And then leave everything else in whatever fraction or whole number we happen to need. And so for making water gas, it'd be H2 plus a half O2 gas, because H2 is the most stable state of hydrogen at room temperature. And then a half O2 for the 1 oxygen atom. And then the delta HF, now you might wonder, how would you ever determine these delta HFs? Well, you notice that the first 2 reactions are kind of like combustion reactions. So the first reaction, what we would do to find the enthalpy of formation of CO2, we would actually just do a bomb calorimetry problem with graphite. So we would just take graphite, combust it in a bomb calorimeter, see how much heat's given off, and work out the kJs per mole. And that's how we would find the delta HF of CO2. If we wanted to do this for water, what we would do is we put hydrogen in a bomb calorimeter. We just have to do it more carefully to figure out how much hydrogen gas we're putting in so we can measure the amount of gas going in. And as long as we did that carefully, we could find the enthalpy of formation of water from that combustion reaction's enthalpy. So we can use like bomb calorimetry to start finding some of these enthalpies of formation. And so water liquid has a different enthalpy of formation because water liquid has a different enthalpy than water gas. And so in fact, you can use enthalpies of formation to find like an enthalpy of a reaction like water gas to water liquid. So if you want water gas to water liquid, so let's say you're curious at calculating the enthalpy for water gas going to water liquid. Can we predict the sign without looking at delta HFs right now? If we predict the sign of this reaction, gas to liquid for a substance should be fast-moving particles having to slow down their energy, losing energy. So this reaction has to give off energy, should be exothermic. So we should predict delta H should be less than 0. So we might be able to predict that delta H is less than 0 from our knowledge of what a phase change delta H should look like. And then what we can do is just plug in our standard enthalpy of formation of our product. So do the product delta HF. And so we have 1 mole of water here, so we'd have minus 285.83 times 1 mole. So that would be just minus 285.83 kJs, and then minus plugging in the water gas, minus 241.82 kJs per mole times 1 mole, because there's 1 mole of water in the reaction. So that's kJs. So it looks like this will still be a negative number. So we have minus 285.83 minus negative 241.82. And that's minus 44.01. So our delta H here from the standard enthalpies of formations of our products minus the reactants. So this minus sign here is just from the products minus the reactants. Notice in every step here it's just a simple delta to find our delta H. And so this works out to be equal to minus 44.01 kJs. And so if we tabulate standard enthalpies of formations for a bunch of different substances, we should be able just to sum up those for the products minus those for the reactants. But let's look at writing some, make sure we know how to write formation reactions. And let's also make sure we recognize that if you have an element in its standard state like O2 gas, so if we try to form O2 gas, it's coming from what we call an identity reaction. It's coming from itself. So it would be O2 gas producing O2 gas, because O2 gas is the most standard state. It is the common state of oxygen. So there's no enthalpy associated with forming O2 gas. So the delta HF of O2 gas here is defined to be 0. Because anytime we form an element in its standard state, it's coming directly from itself already. So that, by definition, would have to have an exactly 0 standard enthalpy of formation. And so we're going to summarize a few things on the next slide of like which elements, how we can recognize elements, and which of their forms, their standard state would have this enthalpy of formation as 0. Then if we're writing the standard enthalpy of formation reaction for something like ozone, ozone being an allotrope of oxygen, but a lesser stable allotrope, it would just be the formation reaction from O2. And then we'd have to have 3 halves O2 to have the right number of oxygens on both sides. And again, remember, fractions are okay. Nothing wrong with the fraction in this equation because we're always trying to form 1 mole of a product. So the formation reaction is forming a substance from its elements in their standard state and forming 1 mole of that substance. For CH4, the formation reaction would be carbon solid, graphite, and then plus H2 in the form of gas. And so what things like our textbook and other sources online have are tabulated standard enthalpy of formation values for lots of different substances. So this allows us to write reactions and ask questions like, well, what's the delta H of the reaction? Well, we would just look up the standard enthalpy of formations of the products and reactants. If we knew all of those, we can plug them in and solve for the delta H of a reaction. Yeah, so the only difference of water is the physical state. So just like we had mentioned previously in like section 5.4 that physical states would change. Like if you change the physical state of a substance, you can change the delta H of reaction.
But how would I get water versus gas and the bomb calorimeter would have to be?
Oh, so what we would probably do is do the bomb calorimeter example. We would get water liquid predominantly forming because the calorimeter would be sealed. And so we would do the experiment. The bomb calorimeter experiment would tell us the delta HF for forming water liquid. And then we would either have to do another experiment a different way where we're doing the bomb calorimetry example where the whole calorimeter is just already above the boiling point of water, or we do some other phase change experiment to find the phase change enthalpy. So there are experiments. We're not going to talk about them. Well, I think they might come up in chapter 11 later for a way to find a delta H of a phase change. But there are other experiments we haven't talked about that you could use to determine the enthalpy of a phase change.
So by seeing an equation, I cannot predict the state of the products.
No, I guess the point of a formation reaction would be if I said write the reaction for forming water gas, you could write the reaction. But if I just said write the formation for water, you would have no idea if it's gas or liquid. But you could write the formation reaction for gas, liquid, or solid, and then you could look up in a book and see tabulated values for their standard enthalpies of formation. Like, so the back of your textbook, or in the end matter on the e-text, has a table that probably has about 1,000 different molecules or compounds standard enthalpy of formation values. And so it's through the ability, yes, tabulate those values that then allows us to use those values to calculate enthalpies of reaction. Okay, so something you might be wondering is, well, which elements, like what are the elements' common states, the most natural or stable states an element exists as at room temperature? A lot of elements are gases, or actually, maybe not a lot, like several elements are gases, things like H2, N2, O2, F2, Cl2 exist as diatomic molecules. We, of course, have the noble gases, which exist as monoatomic gases. It's like helium, neon, argon, krypton, down the noble gas group. And then that's about it for gases. There's actually, we mentioned this before, there's two liquid elements, bromine and mercury. So bromine, Br2 is its form. So the halogens are all diatomic molecules like F2, Cl2, Br2, I2, but only F2 and Cl2 are gases at room temperature. Bromine's a liquid, and then I2 is a solid. And then some other solid elements are most of the other elements. So, you're talking the metals, metallic elements other than mercury. So sodium, calcium, iron, et cetera, would exist with a standard enthalpy of formation of 0 in their solid forms. And then things like carbon graphite that we mentioned earlier, white phosphorus, and what's called rhombic sulfur. I don't see too many examples ever ask you about sulfur or phosphorus because they're kind of peculiar in terms of their nature, but they happen to be solids at room temperature if you didn't know that. And so if you had these elements in any other state, if you have O3, if you have diamond, if you have sodium gas, if you have some other physical state or some other form, some other formula of these substances, then that would have a non-zero standard enthalpy of formation. And so things like hydrogen atom, oxygen atom, diamond, example, some other form of phosphorus. So if you just have some other form of these elements that's not their standard state, then they would have some non-zero standard enthalpy of formation. Then the ability to use standard enthalpy of formations is to, like we mentioned, be able to calculate enthalpies of reaction just from being able to sum up the enthalpies of our products and then subtract the enthalpies of the formations of the reactants. And this is very much like a replacement for, like what we mentioned, if we could tabulate just the absolute enthalpies of substances, then we would just be adding up those for the products minus reactants. And so these standard enthalpies of formations are just replacements for knowing the absolute enthalpies of all these different substances we might want to know to be able to calculate a delta H of reaction. So for example, if we want to find delta H of the combustion reaction CH4 plus 2O2 goes to CO2 plus 2 waters, what you have to do is just make sure to be careful to look at the physical state of the substances so we're grabbing the right values here. So we want to make sure that we're grabbing the water gas, delta HF, and not the water liquid. And so if we want to calculate our delta H of this reaction, we would just be taking 1 mole of CO2 times the delta HF of CO2. So our mole cancels. A delta H of reaction should have units of kJs. The only time you see a reaction or a substance has a kJ per mole is when that enthalpy is kind of a property of a substance. Like the enthalpy of formation is a property of a substance. That's why we're writing the reaction to form 1 mole, so that the enthalpy of the reaction normally in kJs is per 1 mole of that product. So you're getting the property, the enthalpy of formation in kJs per mole of the substance. So a delta H of reaction should usually have units of kJs. So that's how we're making sure to show that we're taking 1 mole for 1 CO2 to cancel out the kJ per mole unit in the standard enthalpy of formation. And so then we're summing up the sum of the products. So we add 2 moles times the delta HF of water gas, so minus 241.82. And then we're subtracting, so doing the delta, so summing up the products, minus the sum of the reactants. If you're noticing, there's a lot of like minus and like plus signs here, so you have to just make sure that when you're plugging this in your calculator that you just, maybe we'll do this together too when we plug it in, just to make sure you're doing not screwing up the minus signs. So an easy mistake here is to lose track and maybe make this minus a plus, but again, just remember you're doing the sum of the products and then minus the sum of the reactants. And so then we're subtracting CH4, so the delta HF of CH4 minus 74.8. And now I could write this for oxygen, and maybe it's helpful just to make sure that a lot of times you're not going to see a tabulated value or a given value for oxygen because we're just going to have to know that its delta HF is defined to be 0. Because oxygen here is in its standard state, in its most stable state of O2 gas. So we have to recognize like the common elements, like phosphorus, sulfur. We're not going to give you those in examples and expect you to remember the form of those that have a 0 delta HF. But for mostly everything else, metals are solids except for mercury. Non-metals are mostly gases except for bromine being a liquid, iodine being a solid, carbon being graphite, being the obvious ones that come up a lot. Okay, and so if we work this out here, it's just in your calculator. I would try to make sure to be very direct of doing like minus 393.5 and then like plus 2 times minus 241.82 and then minus negative 74.8. Like I almost try not to think about the signs. Like in my head, I'm not trying to be like minus is plus. I'm just trying to put it in and being very careful just to do the math directly without having my brain screwed up. Because I feel like my head will make more mistakes than my calculator will. And so I get minus 802 kJs, 802.3. And we had given this value before, and this was like more or less the same value we'd seen several slides back. You know, so when we calculate delta HFs here, we are calculating, you know, sort of an exact value that we should get for the delta H of this reaction. So it's a very precise technique. As long as we tabulate enthalpies of formation, we can use those in reactions to find delta H's of reaction. So it kind of gives us 3 approaches to find a delta H of reaction. We could study it by calorimetry, we could use Hess's law, or we could look up tabulated delta HF values. So those are the ways we have of knowing delta H's of reaction. There's one other technique that we can actually use, but this way ends up being an approximation technique. So we can try to understand bond enthalpies. We can look at a bond enthalpy chart and see how we can use that to approximate a delta H of reaction. But one of the keys is with this technique is it's going to give us an approximation and not always the exact enthalpy of reaction. And so the idea of bond enthalpies is you can get an idea of how strong a bond is by looking at its bond association energy or its bond enthalpy. So for Cl2, the bond enthalpy is about 242 kJs, or the delta H of this reaction is about 242 kJs, which would make the bond strength of 1 Cl2, so the Cl-Cl bond enthalpy, we usually symbolize that with a D symbol. So bond enthalpies, for some reason, historically have taken the symbol D. So the bond strength D of HCl is about 242 kJs per mole of that bond. And so, okay, so that's one bond enthalpy. What about the CH bond? Well, if you atomize CH4, so if you break all these bonds in CH4, so you now have broken all those bonds in CH4, so you have carbon plus 4 hydrogens from CH4, that the delta H of that reaction is 1652 kJs, but we broke 4 bonds in the process, right? So the bond strength here on average would be that value divided by about 4. So the D value, it's not a D, that's a C. So the D value of the the HC bond, or the CH bond, is about, I think that's 413. Yeah, 413 kJs per mole. So you see for the CH bond is that it's stronger than the Cl bond for some reason. When we get into chapter 8, we get a little bit of a predictive value. We can maybe understand some elements of bonding. Like if you imagine a longer bond, it's usually weaker. If you can imagine usually a shorter bond, it's usually going to be stronger. If we get into like imagining double and triple bonds, if you remember those from Lewis structures, like nitrogen has a triple bond, that's going to be a very strong bond. Double bond usually not as strong. But some of those trends we're going to pick up later in chapter 8 and come back to bond enthalpies and try to talk a little bit about their. For now, we can look at a bond enthalpy chart and just kind of see that different bonds have different bond enthalpies. And that if I give you a molecule like O2, you're not going to necessarily know it's oxygen with like a double bond. If I say N2, you may not remember it's nitrogen with a triple bond. So at this point in the material, if we want you to use bond enthalpies, we have to show you Lewis structures like this. So we have to show you that you have CH single bonds or that you have the O2 double bonds. And then you have the CO bond and the water bond here. And then you can see like the oxygen-oxygen double bond is 495. You can see the CH bond that we mentioned earlier, 413. We're forming OH bonds here, 463. And then we have the CO double bond, which is about 799. So we're forming, and we're breaking bonds of one strength, forming bonds of a different strength. And one of the things that's really interesting with bond enthalpies is we get a really interesting way of seeing why it is that a reaction like this is so exothermic. Because if you remember, we just looked at this reaction previously on the last page. It was minus 802 kJs per mole. Well, why does this reaction give off so much energy? Why does it lose so much? Do you think it's because we're forming weaker bonds, or do you think it's because we're forming stronger bonds? It's going to be because we're forming stronger bonds. And using bond enthalpies, we can get a sort of a picture of how much energy it's going to take to break all these bonds in the reactants and get a picture of how much energy we get back when we make the new bonds in the products. And so one thing when we go to try to calculate our delta H here is, one, it's an approximation. It's not going to be a direct equality. So it's only going to be an approximation. It's an approximation because bond strengths vary. You know, like if you have a CH bond in methane, it's not exactly the same as it is in ethane, or if it's in some substituted hydrocarbon. You know, so the average bond strength of CH is about 413. But if you have different types of CH bonds and different types of molecules, they may vary a little bit in their bond strengths. If you have a CO double bond in CO2, it might be 799 kJs per mole, but if you have a CO double bond in some other molecule, it might have a slightly different bond enthalpy. Yes?
So I cannot tell the bond strength by looking at this chart from carbon to hydrogen at 413. It occurs everywhere. It could be different.
Well, yeah. So these are like average bond strengths for this type of bond in most molecules. You know, so it's kind of like an on average value, and specific molecules may vary. And so that's why we're getting an approximation here. And like we're going to see for this reaction here, we're going to get a pretty good answer, and it's because the bond enthalpies are just more closely related to these molecules than they are maybe some other molecules. It's really just making sure we see here that this isn't always going to be an exact calculation. So if you do the same approach but for like a bigger molecule, the average CH bond strength may not be 413. It might be 410, and you're going to be off a little bit. So it'll give you a close idea. But one of the things that we're going to see here is that we're going to sum up the sum of the bond strengths, but of our reactants. So we're going to do a delta here, but doing reactants minus products. I forgot to put the D in. So we're summing up the bond strengths of the products. So reactants minus products. But this is almost like a Hess's law problem. And if I were to go back a minute to enthalpies of formation, and I, like sometimes I take the time to show this with bond enthalpies, I really don't think, and to be honest, I think it's more confusing than it is helpful. But if you go back to bond enthalpies and imagine writing out the enthalpy of formation reactions and then rearranging them and doing Hess's law, then that's why you're summing up the products minus reactants. And so so for the previous example, we had CH4 plus O2 goes to CO2 plus 2 waters. You could have taken the 2 water formation, so form 2 waters, form a CO2, and then take CH4, flip the reaction to have CH4 on the reactant side, and you're just doing a Hess's law summation. And that would sum up to the combustion reaction, and the answer would have been doing the delta HF of the product times 2 times the other product minus CH4. So you would get the actual approach that we're using with the equation. But with bond enthalpies here, it's just, notice that the bond strength is a property of the reactant, not the product. And so because of that, what we're doing here is we're sort of saying, well, how much energy would be associated with taking CH4 plus the 2 O2s to their atoms, so sort of atomize your reactants. How much energy does that take? And that's always going to take energy, right? It's always going to be an endothermic reaction. Like if you're breaking a bond that exists, you're always going to have to put energy in. Like that's never going to be exothermic. Because every bond that forms is stable. It wouldn't have formed if it's not stable. And so the only reason a bond can form is because it adds stability. So to break the bond, you have to break that stability. And so it has to be endothermic. Okay, and so the question is, or with the bond enthalpy chart, you can figure out precisely, or maybe a better word is approximately, how much energy that should take. And so that should take 413. So the delta H to break these bonds should be approximately equal to 4 moles times 413 kJs to break the 4 CH bonds. And then plus 2 times 495 kJs to break the 2 O2 bonds, because O2 is 495 kJs. And so to break those bonds, definitely endothermic. And that's 2642, and that's positive, of course, so plus 2642 kJs. So 2642 kJs. So it takes that much energy to break the bonds, and then we're getting energy back when we make the new bonds. Like making a bond should be exothermic. So if we make new bonds, so we take the carbon plus the 4 hydrogens and plus the 4 oxygens, and we now recombine them in a different way. So we now make the 2 CO2s, and we make the 2 waters. Or excuse me, we make just 1 CO2. So just 1 CO2 gets made. So we just have 1 CO2 in our product. But that 1 CO2 has 2 carbon-oxygen double bonds. So the carbon-oxygen bond strength is really strong, 799 kJs. So we're making 2 of those bonds. So how much energy do we get back when we make the new bonds? Yes? Let's finish the analogy of how much it takes to break the reactants and then come back to that question once we see how much energy it takes to form the products. And let's come right back to that in a minute. And so imagine we ask the question differently. How much energy would it take to break the bonds in CO2? Like if you're breaking the bonds in CO2, if you're breaking the bonds in water, you're going back to the reactants, but you're also just saying, almost in a different case, like in fact, let's rewrite this and we'll see why we need to flip this reaction in a minute. Let's just take our products and write it like this. Let's take our CO2 plus our 2 waters going to carbon plus 4 hydrogens plus 4 oxygens. It's like, so how much energy does it take to break those bonds in CO2 and water? I just asked the question that way. And so this is going to take 799 times 2. So we have these 2 bonds here are 799 kJs per mole. And so we're going to have the delta H here is 799 kJs times 2. And then plus making 4 of those OH bonds. So 1, 2, 3, 4. And the OH bond strength was 463 kJs. So I didn't bother writing 4 moles times kJs per mole, and the moles would cancel. So I'm just kind of going 4 times kJs per mole, knowing that I've lost the mole, because it's 4 moles times the kJs per mole. So that's 3450. So what that comes out to. And so now let's think about which one we want to add, which one we want to subtract. And so, because doesn't this look like a Hess's law problem of taking, if we're trying to add these reactions up and have them add up to CH4 plus O2 goes to CO2 plus water, then which reaction would you flip? Would you flip the reactants reaction, or would you flip the products? Or excuse me, would you flip reaction 1 or would you flip reaction 2? You flip reaction 2, because that would put CO2 and water onto the correct side. So we're going to flip reaction 2. And so we need to flip the reaction, we flip the sign. So we have minus 3450. So we have the sum of the bonds and the reactants minus the sum of the bonds and the products is just what falls out from applying Hess's law. So the reason why you would do the delta here kind of backwards for reactants minus products is just because of the way Hess's law is working here. Is because you're taking the approach of how much heat does it take to break the bonds, that's however much energy it takes, then subtracting however much heat you get back from when you make the new bonds. So it really becomes a question, and the utility here, the value of doing this is seeing that the reaction is exothermic here because we're making stronger bonds. Like notice that the bonds in the products have to be stronger. That's why it takes more heat to break those bonds. So the products bonds are stronger in this reaction. If we do the math, 2642 minus 3450, we get minus 808. Again, approximation. If you notice, it should have been 802, so we got close, but we didn't exactly get 802 that we had on the previous slide. Bond enthalpies also don't take into account phases, so it's kind of confusing if water is supposed to be a liquid or a gas. This chart really works where all substances are gaseous, so that's good. If all the substances are liquids or something, the bond enthalpy chart is probably making a mistake at that level. But the bond enthalpy chart, the value here is really seeing that the reaction is exothermic. The reason why this reaction comes out to be exothermic is because the products bonds are stronger. If you form stronger bonds in the products, that's going to lead heat to being released. An endothermic reaction is going to be the opposite. An endothermic reaction, by definition here, is going to have to be forming weaker bonds. So it gives you an idea of what it is to be endothermic versus exothermic. Is just, it all has to do with the relative strengths of bonds. So if we're forming a stronger set of bonds, more stable molecules, more heats can be given off in that reaction. And so it gives us a sort of a reason or a picture on a molecular level for why a reaction like this is exothermic. Just has to do with the differences in bond strengths. Yeah?
When you flip it and add it, you don't only go through, but you start with 2 O2.
Well, so if you flip this reaction here, you would have these atoms on the reactant side, which would match these fragments on. So when you flip the reaction, you're canceling out the atom fragments.
Right up, I get that. But
All right, let me.
there's 2 O2.
Oh, I see what you mean. Yeah. So I just forgot to write the 2 in here. So yeah, so this should have a 2 here, and I was just going to make sure that we're seeing that when we flip the reaction and go to CO2 plus 2 waters, that's how we're adding up here. And then yeah, I just forgot to carry the 2 over here. Okay. And so reactants minus products comes out here for really, I would say 2 reasons. One, Hess's law. You can, if you just think of how Hess's law applies, you're taking reactants to fragments, fragments to products, and if you sum up the delta H's, the right answer would come from breaking the bonds in the reactants, so the bond strengths of the reactants, then minus the products. And then the other way is thinking that enthalpies of formation are a property of a product of a reaction. The bond strengths are a property of a reactant. And so that's kind of why the analogy flips. And so because standard enthalpies of formations are products or properties of a product of a reaction, we can then use products minus reactants. Because bond strengths are the property of the reactant side in a reaction, it's the molecule going to fragments, so it's the thing going forward, so it's for the reactants to products, why the bond strengths would be reactants minus products. Okay, so another analogy here, if you break bonds, it takes energy. If you form bonds, you get energy back. And so that's what we're seeing here. How much energy to break the bonds? So starting from our CH4 plus our 2O2. How much energy does it take to break the bonds to our fragments? And then how much energy do we get back when we make our CO2 and 2 waters? And so this was plus 2642, and then this was minus 3450. And so it's just seeing how much is the relative difference here. If we have a different reaction that takes less heat, less energy to break the bonds, and we get less energy when we make the new bonds, and that would be an endothermic reaction. So you can get an idea in a picture for why some reactions are exothermic versus endothermic. Okay, so we started this chapter, or maybe even the class, because we did this in the first day of class. We started an analogy with like hydrogen and oxygen reacting together, and they do that big kaboom. You know, we saw a balloon filled up with this. And so then, which statement is true? Like, why did we see this violent combustion reaction? So read through the answers and try to think through which one you think is best. I'll let you think for a minute or two. Okay. Do we all agree that the answer is A, or mostly agree that A sounds pretty good here? That the reaction is giving energy off. So the reaction definitely gives off energy. It doesn't absorb energy. We're giving off a lot of energy in this violent combustion reaction, and it's because the products bonds are more stable or stronger. So more stable is just another way of saying stronger. So a more stable bond would be a stronger bond. So the products bonds have to be stronger in order to give energy off. And so if a reaction absorbed energy, then the exact opposite would be true. The products bonds would be weaker or less stable. And so the reaction is definitely giving energy off. It's definitely not absorbing energy. And then the reactants bonds are not more stable than the products. The reaction gives off energy because the products bonds are stronger, more stable. Okay, there was one more question. I'm going to say we do some review problems later, so we'll come back to that last problem hanging in chapter 5 a little bit later. And so I want to get into chapter 6 now. So chapters 6 through 9 kind of start a unit of trying to understand the electronic nature and some of the molecular structure of molecules. So we start off chapter 6 by trying to understand really what's going on with electrons and atoms. So chapter 6 is about the electronic nature of matter, what the electrons are doing to the best that we can say or approximate in atoms. Chapter 7 will go through some nuclear trends. So it's kind of interesting in chapter 6, we almost make it seem as if all atoms are the same, you know, because they all have electrons that behave in similar type orbitals. But obviously, nuclear trends matter. The nucleus plays a big role in whether an atom's like sodium is a metal, or if it's like neon and it's a noble gas. And those are just two elements right after each other on the periodic table. And so the actual behavior of elements has a lot to do with their periodic properties, and those properties have a lot to do with just the way the nucleus interacts with those electrons. And so that'll be chapter 7. Chapter 8 gets into concepts of bonding, so ionic and Lewis structures, so structures of, bonding and ionic compounds, and then simple bonding in molecular compounds. And then chapter 9, we get into like three-dimensional structures, so trying to predict the actual shapes of molecules and some of their properties. Okay, so for chapter 6, kind of the basic layout of this chapter is we talk about the wave nature of light, quantized energy levels, photons. So we start the chapter off talking about light. Turns out light and electrons have some things in common with each other. One of the big things in common with each other, if you've taken either physics or seen this in other chemistry classes, is that light being a non-particle, or being a particle without mass, or being a massless propagation of energy, that it behaves in some ways like a particle. So light has a wave-particle duality, where it behaves like a wave, or is a wave, but also has a particle description in some of the ways it behaves. And then also an electron is an actual particle, it has a mass, but then it also behaves as a wave. And so they have a lot in common with each other in that regard. And so then we also talk about how we came to know some features of the hydrogen atom and its emission spectrum, and how that goes into trying to understand things like orbitals and electron configurations for bigger atoms as we go through the chapter. This red versus gray doesn't mean anything other than I forgot to change the coloring for once when I taught over a summer and one lecture was all the red. And so we're covering everything on this slide. The gray is just things that will come up later in the class, or later in the lecture, so into next week, on orbitals, what they look like for bigger atoms, and electron configurations. Okay, so if we start off with the wave description of light, so light can be described by its wavelength, its frequency, and the speed of light, of course. And so the number of waves passing a given point per unit time is the frequency, and then the wavelength is the length in space that it takes to complete one of those frequency cycles. And so the speed of light that light travels at is c, is equal to the wavelength lambda times the frequency. You may or may not have seen this equation before, but this would be our wavelength, and this would be our frequency. The speed of light has units meters per second, so our wavelength has units of length like meters, and the frequency inverse seconds. So that we do meters times inverse seconds and get a speed of light out afterwards. And so from like a photon of light for A versus B, traveling, say this is, from 0 to 1 meter, both of the photons would reach 1 meter in exactly the same amount of time, because they're both traveling at the same speed of light. And so both photons would reach point B. So let's say point A is our starting point, point B is our ending point. They're both going to reach the ending point at the same moment in time. It's just one of them is going to have fewer wavelength cycles complete, and then the other one's going to have more wavelength cycles complete. So in photon B, we have a shorter wavelength, but then we're going to have a greater frequency. So we're going to have more of those cycles complete per unit time. And then the upper part has a longer wavelength and therefore a lower frequency. So we have fewer frequencies completing per unit time. And the frequency unit, it's symbol not V, but it's nu. So it's that Greek letter nu. So let me, in fact, it has a little bit more of the arc this way than just a simple V. So H nu, so C is equal to lambda times nu, you'll hear is what this equation is equal to. And all light travels at the same speed, the speed of light. Now, the speed of light can vary in different media, but if we're talking about light both traveling through air or through a vacuum, it would travel at the same speed. Okay, and so then we can describe light by its relative wavelength or frequency in terms of if we have really long wavelength versus very short wavelength light. And then by corollary, if we have a long wavelength, so if we're looking at radio frequencies are characterized by having a very high or very long wavelength. So we have light of a very long wavelength, then in the same unit of time, we're going to have a very low frequency. So light with a very high wavelength has to have a very low frequency. So the frequency here is on the lower side, while the wavelength is on the high side. And so radio frequencies, this long wavelength, is probably not so bad. We're going to start thinking about, do you want to encounter a long wavelength photon? Would you rather encounter the opposite side of the electromagnetic spectrum, a gamma ray, which has the opposite, a really short wavelength, so a wavelength really short, and a lot of frequencies per second. So would you rather this pass through you? Would you rather this thing pass through you? Probably the radio frequency. So if we're going to build cell phone towers, probably better we use radio frequencies and not gamma rays, So gamma rays are going to burn our skin a bit more than, say, radio frequencies will. And so gamma rays characterized by a very low wavelength, but then by a very high frequency. So a lot of cycles per second. And so remember, they both have the same, so a radio frequency light photon versus a ray of light with a gamma ray, they both travel at the same speed of light. And so because of that, that's how we can have a connection between having, if we have a long wavelength, we have to have a short frequency, and then by corollary, if we have a very small wavelength, then we have to have a very high frequency. And so then if we look in the middle of our two extremes, I think it's always helpful to remember radio frequencies. You could probably remember they're going to have the long wavelength. That's what you would rather have pass through you than the shorter wavelength, greater frequency. And so the high wavelength radio frequency are on one side of the spectrum, and then the low wavelength, high frequency on the opposite side. And then everything else is in the middle. So X-rays, still high energy. Ultraviolet light is less energy than ultraviolet, but still relatively high in energy. And so you can kind of see here that we're just going to that longer wavelength as we increase from gamma to X-ray to the ultraviolet. The visible region is a very narrow region of the electromagnetic spectrum. It's just from 400 to 750 nanometers. That would be 400 to 750 times 10 to the minus 9. Meters in terms of their wavelengths. And if you've ever wondered, like, why do we see in the visible? Well, if so ultraviolet rays are bad. I think we all know this, right? When you're out in the sun in the summer, they can cause damage to your skin, give you sunburn, give you skin cancers, and it's the high energy light breaking bonds in your DNA. So ultraviolet light has enough energy to start breaking bonds in your DNA. Wouldn't it be great if you saw that light as really bright? Isn't that perfect, right? So you want your eyes to tell you when something's really bright so you don't go into it, so you go away from it. And so if for some reason our visible spectrum was in the IR region, then we would be out in the sun all day long and never realize it. We'd be blind to it and be doing all kinds of damage. So it's really perfect that the visible region is right up against the region of electromagnetic spectrum that is really damaging to us, so that we can sense that and get away from it. So as you get towards the 400 nanometer side, and a bright light source, it starts to get really bright and intense, and you would want to, like I said, not look at it, like the sun, for example. And so, so then from there we have the infrared, the microwave, and then that radio frequency region. So we can sort of think about the spectrum in terms of the relative energy of the spectrum from the low energy side on the radio frequency to the high energy side. And in some ways we haven't even yet really talked about how we know the energy of a photon of light. We're going to see an equation in a minute that lets us calculate the energy if we know the wavelength or the frequency of light. But we're going to see that the low energy side is our radio frequency, the high energy side, the gamma ray side. And so the thing that I would just more or less not necessarily memorize the cutoffs of these regions is just kind of memorize the ordering that we have. You know, sort of the gamma ray to X-ray to ultraviolet to then the visible, then the infrared, microwaves, and then radio frequency. And the only cutoffs I would really think are worth knowing are that 400 to 750. But we're going to see those a bunch of times. I think that'll be pretty obvious, the visible region from 400 to 750 nanometers. Okay, so let's just do a couple calculations. And so, and then we haven't quite, you probably know the speed of light's 3 times 10 to the 8 meters per second. I like to use 2.998 times 10 to the 8 meters per second as my speed of light in the vacuum. You can look up more precisely than this, but I think that this is what, since I usually use values to 4 sig figs, that this is the one I commonly use in problems. But so what is the frequency of light if the wavelength is 725 nanometers? And so if C is equal to lambda times nu. Nu has units of inverse seconds. That's the hertz. So 1 hertz is equal to 1 inverse second. It's kind of a strange unit to get a name that's really just a simple inverse of seconds. But hertz is just, an inverse seconds is 1 hertz. And so then speed of light's equal to lambda times nu. We're trying to solve for nu. So C divided by lambda. So nu would be equal to 2.998 times 10 to the 8. I'm going to do something funny. I'm going to just divide this by 725. Now, what's funny here? Like, this is how I see a lot of problems when students come in, like after a test or something. Like, I don't know, I got the answer wrong. You got to write units in, right? So as long as we're writing in our units, we're going to see that we have to convert either our speed of light to nanometers per second, which I think would be kind of weird, or convert the nanometers for our wavelength into meters to cancel out our units. So in order to cancel out meters and meters per second, we have to convert nanometers into meters. And so then we have to remember the conversion, that 1 nanometer is really small, right? So it's 10 to the minus 9. Hopefully we remember 9 for nano, but then it's 10 to the minus 9 meters, as opposed to, remember on a test, you're usually going to be stuck with, is it 10 to the plus 9 meters per nanometer, or is it 10 to the minus 9 meters per nanometer? Nanometer is really small, so it's 10 to the minus 9. So we do 2.998 e to the 8 meters per second divided by 725. What I do here is a 725 e minus 9. So I can put that into a calculator, because that would be 725 times 10 to the minus 9. You can obviously do that a few different ways. You can do 725 and then times 10 caret minus 9. Remember, calculator issues, sometimes we make mistakes on these types of exponentials. Let's make sure that we're not just making a calculator error whenever we encounter these type of problems. But I get 4.14 times 10 to the 14. And so my units, inverse seconds. So I had divide by seconds from my speed of light that didn't cancel out. And so that's where we get inverse seconds from. And that's just the unit of hertz. So 1 inverse second is a hertz. Okay, so calculating frequencies, pretty straightforward. Just C is equal to lambda nu. Yep.
So you don't like flip the sign converting from hertz to meters per second, so it's kind of same.
Yeah. Yeah, so we don't like the even though the hertz doesn't have like an inverse unit, it's still 1 hertz is 1 inverse second. So if I was doing this directly, I might do the inverse second is 1 hertz. This is 1 inverse second equals 1 hertz. So let's look at this one here. So compared to 725 nanometer photons, what is true about a 625 nanometer photon? So the radiation has a greater frequency. The radiation travels at a lower speed of light. Statement 2 is obviously incorrect, right? They both travel at the same speed of light. So both photons travel at the exact same speed, so statement 2 is not true. And then if we're thinking C is equal to lambda nu, if we go to a lower wavelength, do you see how we have to have a greater frequency to get that same speed of light come out? So the frequency has to be higher. So the radiation for a 625 nanometer photon compared to that 725, the 625 nanometer photon has had that greater frequency. And so that statement would be true. Okay, and so an experiment was done. This is actually done by Hertz, and this is kind of why his name gets put on some units and things like that. It was later then explained by Einstein, so Einstein gets credit for explaining why this happened, is that if you shine light onto a metal, you can cause electrons to be ejected. And so at first glance, this was somewhat strange because light not carrying a particle is somewhat strange that you could get a particle to be given off. So it was as if light could almost behave like a particle, but it turned out only under certain circumstances. It was only if the light had a sort of high enough energy. It turned out it had to have a high enough frequency. If you use too low of a frequency, even a very bright light source, nothing would happen on the metal. And so black body radiation was sort of also found to be interesting. Black body radiation is the idea that you can have things glow with different colors, and the colors that they glow at are related to their heats. And so black body radiation kind of was looking at, say, flame temperature. It's like a blue flame versus an orange flame. Think of a Bunsen burner. Which flame's hotter? Like if you have a Bunsen burner, would it be hotter if it were like yellow kind of up here, or blue when it's like almost making like that sound it makes? The blue light's hotter. and the orange flame is cooler. It's still hot, but it's a cooler flame. And so the color was then being related to temperature. So how could color be related to temperature? Well, color is related to temperature because the energy of a photon varies with its color, and the color varies with its wavelength. And so let's get into this next time, so I don't think we have enough time to finish this discussion today. But the color is related, like the wavelength and frequency is related to the energy of the photon. And so we'll see how so on Monday. Have a great weekend, guys.